Hello, good evening. Yeah, my name is Vlad, and usually I'm associated with this monkey right here, which is me while I was writing that book. By the way, who here has already read that book? Okay. First of all, two people with your hands up, you're awesome. The rest of you, you're awesome as well. But you know what you have to do, right? I don't have to say it aloud. Okay. Yeah, so I'm domain-driven design fanboy, but today I don't want to talk about it. Instead, I want to talk about another subject that I'm really passionate about. In fact, I'm so passionate about that I ended up doing that stupid thing of writing another book. This one was supposed to be published 2 years ago, but I'm a software engineer, so being bad at estimates is a part of our job, so I'm not the one to blame. Anyway, the manuscript is ready, it's almost in production, but anyway, today I want to give you a preview of this book's material. And by preview, I don't mean, like teaser, just to get your interest to pre-order it, no. I want to give you some practical tools that you can apply in your day-to-day job on Monday morning. So, coupling. Don't know about you, but I've always been told that coupling is bad. If you go to a Twitter account of any tech bro and you scroll long enough, I guarantee that you are going to find a post saying something along the lines of, "Remember, youngster, coupling is bad, but cohesion is good. Therefore, always avoid coupling and always strive towards cohesion." That's it. Now, following this simplistic thinking, usually we end up doing something that I call decoupling everything. We want to try and break all systems apart into those tiny components, and these boxes, they can be anything. They can represent classes, objects, microservices, serverless functions, whatever. The underlying idea is always the same. We want to be able to evolve each one of these small parts independently. However, when following this decomposition heuristic of focusing on the size, what results are we getting? Well, usually we go from coupled piles of code to distributed piles of code. And that's not surprising because, as my friend Matthias says, as small as possible is almost universally bad advice in software design. Also, as Nick Tune puts it, there are many useful and revealing heuristics for defining the boundaries of a service. Size is one of the least useful. And yet, of course, we keep on doing that. So, in the next 40 or something minutes, what I want to do is define what is this thing that we call coupling. Then I'm going to show you how coupling manifests itself in software design. And finally, I'm going to combine those insights to try to convince you that we can use coupling as a tool for designing modular software systems. So, first, what is coupling? If we go back to the lexical origins of that word, it will take us all the way back to Latin, where it was composed of co and appare, coapere, meaning fasten together. That simply means that if two things are coupled, they are connected. If you look at any system, whether it's a software system, a car, a mechanism, a city, company, or an organism, all these systems are held together by coupling. Because let's say we take a system and we decouple all of its components. Is that a system? No. That's just a bunch of components that share some boundary, but they cannot work together. And that doesn't make a system. For a system, we need those connections. And those connections, they are actually making the value of the overarching system greater than the sum of its parts. So this approach of trying to decouple everything doesn't make any sense, because if we succeed in doing that, we will end up with something, but not a system. Therefore, I think we can safely say that coupling is an inherent part of system design. So instead of trying to eliminate it, let's try to evaluate those inner component relationships and see if they're working for us or against us. And if they're working against us, then use same coupling to redesign those integrations so that they will work for us. Let me show you what I mean. Let's say we have these two components. This downstream component depends on and thus references the upstream component. That line between them, it represents that connection. It represents what's going to happen if we apply a change in the upstream component. What are the chances that that change is going to break the integration and cause cascading changes in the rest of the system? In other words, the way the components are integrated, it defines what changes can we make in the upstream here without being afraid to break the integrations with other components. Now, to evaluate the effect of coupling, we have to understand its dynamics. We have to understand how it works. The thing is, we are usually bombarded with the simplistic thinking about coupling, as if it's binary. It's there or it's not, that's it. No. In fact, coupling is multi-dimensional phenomenon. We can observe its effects in 3 dimensions, in the dimension of time, space, and the combination of these two, gravitational force that pulls the connected components together. I call it strength, and let's start with that one. So strength defines what is the impact of a change in one component is going to be on other components of that system. The higher the strength, the more cascading changes will follow. Now, how can we evaluate that strength? Well, let's start by thinking about 2 connected components. So we have component A connected to component B. And there is no arrow here. It doesn't matter which references, how they're integrated, whether it's synchronous or asynchronous, doesn't matter. Also, I used abstract term component, so it will be true for classes, objects, services, systems, whatever. The underlying ideas are still the same. So I want to ask you, when we have that pipe connecting these 2 components, what flows through that pipe? What is the energy that's being delivered across these components? Data. Yeah, data, of course. Of course, they have to exchange data. They have to issue commands to do something, or they have to ask for some information about the state of the second component. However, that's not the most interesting thing here. What else? There's something else that is being exchanged between coupled components.
So the functional dependency.
Functional dependency.
A feature that depends on some low-level system function.
Yes, that's true, but let's see if we can find a more abstract term for that. Health check. Yeah, that's a runtime concern. Contract. Expectations. Yeah, what else? System state. Well, that's sort of data. But we have contract over here. We have functional dependency. What else?
Organizational dependency.
Organizational dependency. Yeah. Entropy. Oh, yeah, that's spread fast. Yeah, that always happens. There's this design principle called dry, do not repeat yourself. And it's funny that people always repeat it. What is it about? People usually say, don't repeat yourself. It's not about code, it's about...
Like using some shared solution. Using some shared common component to use it.
Yeah, you're close, you're close. Yeah, it's about knowledge. And that knowledge can be something. It's not defined. So don't repeat yourself. People often say that this principle is not about code, it's about knowledge. But yeah, that knowledge is important. However, we have to categorize it. We have to categorize that knowledge, and we'll get to your answers about contract and functional dependencies soon. It's very related to this topic. But first, small history lesson. As our industry evolved, there were a few models that were introduced to evaluate that knowledge, that strength of a connection. First one was in the late 60s, the model of coupling in structured design. Anybody here familiar with structured design? Oh, two hands, okay. And 30 years later, a model called connaissance. Anybody here is familiar with connaissance? One hand. Anybody is using connaissance in their day-to-day job? And that's exactly why 30 years later, I think we should start thinking about another model of evaluating coupling or evaluating strength. So yeah, this model, I called it integration strength. Basically, it's a remix of these two models. So this one uses terms from languages you don't want to know, like COBOL, Fortran. Yeah, friendly stuff. Connaissance, on the other hand, it's more oriented towards object-oriented programming paradigm. And we need a model that can go across that boundary, that can work with other paradigms. And also, these two models, they cannot be used exclusively because some aspects are covered by structured design, some are covered by connaissance. So we need both of them, and the first one is COBOL and Fortran. Oh my god. Connaissance, it's not friendly as well. Integration strength combines them. It compresses them as well. Coupling and structured design has 6 levels. This one has, if I remember correctly, 11 levels. Integration strength combines them into 4 basic levels: intrusive, functional, model, and contract coupling. Now, intrusive coupling, what do you think? What this one is about? What knowledge it shares? All of it, yes. Yeah, all of it, exactly. Yeah, so intrusive coupling is all about using something that wasn't intended for integration. For example, let's say you are using reflection to read the value of a private field or call a private method. It's private for a reason, don't touch it. But you are introducing intrusive coupling by using reflection. Or let's say in microservices, people usually say that you shouldn't access another microservices database directly, but only through its public interface. And you're still doing that. In that case, that's intrusive coupling as well. So overall, if you're using something, if you're integrating through something that wasn't intended for integration, for example, private interfaces, implementation details, etc., you're introducing intrusive coupling. The practical implication is that such integration method is fragile because, come on, implementation details can change without the authors of the upstream even knowing that you're using them. And it's implicit. It's implicit, yeah, because you're not going to say, hey, I'm going to use your database. So yeah, with this type of integration, we have to assume that all knowledge is shared. Any change in the upstream has the potential to break the integration. Next one is functional coupling, the one that you mentioned. And here we have two components that share functional responsibilities. For example, let's say that they're implementing closely related business logic. Business logic that is going to be affected by the same changes in the business requirements. Or in domain-driven design terms, we're saying subdomain is an example of functional coupling because subdomain is a collection of closely related use cases. Use cases that, for example, work on the same set of data, or overall they're affected by the same changes in the business requirements. Did people here? Come on. Yeah, we talked about it. You know what to do. Yeah, so in DDD there is this concept of an aggregate, which is a transactional boundary that encompasses multiple classes or objects. In that case, that's a rather extreme example of functional coupling. An even more extreme example would be duplicating the same business rule or logic or algorithm in multiple components. if those components implementing that shared business logic have to change simultaneously, then we have an extreme case of functional coupling. And in that case, by the way, they don't have to be connected physically. That's like a wireless coupling, next step coupling. They still have to change together, but yeah, it's quite implicit. So yeah, overall, this level of coupling is implicit. It's prone to cascading changes. Whether it's good or bad, we'll talk about it in a few minutes. Next one is model coupling. And if functional coupling was about sharing business behavior, this one is more about sharing the data structures that used to model the business domain. Now, again, I'm wearing my DDD hat right now. In domain-driven design, we keep saying that modeling is a crucial part of software engineering, and if you can improve the model, go and do it. However, if you have model coupling between multiple components, well, suddenly you have to modify multiple components to improve your model. And of course, well, yeah, I've been there, I've done that. Okay, I'm going to modify a few services now, come on. That model is good enough. Yeah, so model coupling is all about data structures that are used to represent the business domain. And its practical implication is that it hinders the evolution of the model. And finally, contract coupling, the one you mentioned. This one is about two components, or more than two components, that are integrated through an integration-specific model that was formulated with that integration in mind. The idea is that that integration model it's a model of a model. It encapsulates your implementation model. You can evolve your implementation model. And as long as you can translate your new version to the same integration contract, well, the consumers won't even know that you've changed anything in your upstream component. So that's the lowest level of integration strength. Now, if we compare them, just a second, if we compare them, here we have intrusive coupling, which shares all the knowledge. Functional coupling, it changes the shared knowledge from how it is being implemented to what is being implemented. Then we have model coupling that shares the model. And finally, we have contract coupling that reduces that knowledge to an integration contract. Now, contract coupling, by the way, there are quite a few patterns that are basically for modeling that integration contract. For example, facade can be seen as one example, DTOs, another one. In domain-driven design, we have open host service or anti-corruption layer. There's quite a few patterns that their goal is basically to introduce that integration contract that's going to encapsulate the underlying implementation model. Yeah, you had a question?
Yeah, do I understand correctly that intrusive coupling is the strongest and the constant coupling is the weakest? Is it like the gradation of from strong to weak?
Right now, let's focus on the shared knowledge, how much knowledge we are sharing. Whether it's good or bad, you know what, that's going to be my next question. One more thing, before the question, this scale also reflects the explicitness of the integration. Here we have the most explicit interface, that integration contract, and as we go along, we get implicit interfaces, which culminate in intrusive coupling. So yeah, back to your question, or now my question to you. Let's say that, yeah, I have to switch to another slide. Let's say that we have that intrusive coupling between two components. Is this necessarily good design, or is it necessarily bad design? Who thinks it's good design? No one? Who thinks it's bad design? Okay. Who thinks it depends?
I would say it depends.
Consultants, yeah. So what it depends on? Okay, before we get there, you know what? I think we have time for an example. Yeah, so a little example of these integration strength levels in action. Going back to microservices, yeah, we know that sharing a database is a big no-no in microservices world. However, is sharing a database is necessarily bad? So let's see. Come on. Yeah, it works. So let's say that we have two microservices and that database was never intended for integration. In that case, of course, what we have is intrusive coupling. If, on the other hand, we have two teams implementing two components and they had that conversation and they understand that they have to work on the same data, they have to implement the same business rules, so they decided to do that against the same database. Then we have functional coupling because it's no longer intrusive. They know about that database that is being used by multiple services. However, let's say that this component A here is a BI department. And what do they love to do? Well, they love to take all the data from an operational database and use it for analysis. What they're doing is they're coupling themselves to the model that's being used internally by the operational system. So now we have model coupling. And finally, what if this database includes data that is there for integration purposes only? And it's designed in such a way that other services, other components will be able to connect to it and take the data. In that case, that's contract coupling. And if you're familiar with data mesh approach, that's how it works there. They're using database for sharing analytical data. However, that's not an operational database. That's a database that contains integration data only. Okay, so we decided that intrusive coupling is not necessarily bad, that it depends. Let's see, maybe it depends on the dimension of space or distance. The thing is, we can observe connections between components, connections between modules of software across different distances. We can have coupling between different statements, methods, classes, namespaces, components, microservices, or whole systems. The farther we go on the right here, the greater the distance. Now, what about that vertical axis? What is the implication of the growing distance here? What do you think? In terms of coupling? Strength? No, not strength. Let's say we have abstraction. Yeah, so these are levels of abstraction. Yeah. What is the practical implication? Let's say you have to modify business logic that is implemented in coupled methods versus in coupled microservices.
Complexity of the project itself, like the risk of breaking something.
Yeah, it's close. Yeah, so I'm not going to torture you anymore. Yeah, that's close enough. Yeah, so that's actually the coordination effort that's required to implement a change that affects both coupled components. In other words, if the upstream changes and causes cascading changes to the downstreams, the farther the distance between them, the higher the coordination and collaboration effort that will be required to actually implement that change. So what we can say is that the cost of change is somewhat proportional to the distance between those coupled components. Now, that's not the only interesting effect of distance. There is another one, which is inversely proportional to coordination. And that's lifecycle coupling. Here, on the other hand, the closer connected components are, the higher their lifecycle coupling. Usually, if they're located close to each other, that means they share the same lifecycle, and they will have to be developed, tested, and probably deployed together. So, on the other hand, on one hand, we have coordination effort that grows with distance, and on the other hand, we have lifecycle coupling, which reduces with the distance. Again, microservices probably don't need to be deployed together, while classes or methods are. Okay. Now, another interesting aspect of distance, you mentioned levels of abstraction. It's not the only thing that affects distance. The structure of the organization that implements the software also affects distance. Let's say that we have two microservices that have to be changed together. Now, consider two cases. In the first case, those two microservices are implemented by the same team, or in the second case, they're implemented by different teams. In the second case, we'll have higher coordination effort. We'll have lower lifecycle coupling. So overall, we can say that the distance between them is greater. So distance is the function of both levels of abstraction and the social technical aspect of software design, the structure of the organization. Okay, now, let's say that we have this awesome design right here. So we have two components, functional coupling between them, almost the highest level, and these components belong to different systems, which means the distance between them is great as well. So if we have to implement a cascading change, it will require high coordination effort, and functional coupling probably means that there will be quite a few of those cascading changes. Is this design necessarily bad? Is this design necessarily good? It depends. Okay. Yeah, you got to check. It depends. It depends on another question we have to ask. It's sort of, if a tree falls in the forest, nobody's around to hear it fall. Does it make a sound? No, probably makes some vibrations of the air. And same here. If that upstream component, which is one of them, never changes, are we really going to feel the effect of that coupling across that immense distance? So when evaluating the effect of coupling in software design, we also probably have to ask, well, that upstream component, will it change? Or how frequently will it change? And predicting future, of course, is not trivial, but we have a few models that can help us to evaluate or predict the rate of changes. One of them is Worldly Maps. Another one that I'm familiar with is Domain Design's subdomains. And guess which one I'm going to show on the next slide? It's not Worldly Maps. Yeah, so in domain-driven design, we say that a business domain is usually composed of those business building blocks, which are sets of coherent use cases. Use cases that work on the same data, that change together, etc. What's interesting for us here is that not all subdomains are the same. If we analyze their business goals, they can be categorized into three types: core, generic, and support. Core subdomains are all about the company's competitive advantage, or how the company is making money. Here we can find inventions, optimizations, intellectual properties, or other complexities that are unique to the company. If, for example, a competitor steals the implementation of your core subdomain, not good, because that's no longer a differentiator for you. So again, core subdomains are all about those things that make your company unique, that make it stand out against competitors, other players in the same industry. Generic subdomains are the opposite. Here we have solved problems. If these were interesting problems, here we have solved problems. Here we have functionalities for which we can use an existing solution. For example, we can buy an off-the-shelf product, we can use an open source solution, or a service that somebody provides. Implementing that in-house wouldn't produce a solution as good as the one that is already battle tested. So according to domain-driven design, generic subdomains, hey, you have the solution, go and use it. And finally, supporting subdomains are somewhere in the middle between those two. As core subdomains, you have to implement them in-house, you cannot use an existing one, but as generic subdomains, they do not provide any competitive advantage, so there is no business value there. How come? Well, usually these are simple things like CRUD data entry screens or ETL jobs, things that's, well, if core subdomains are interesting problems, here we have soft problems, these are boring problems. These are things that are just annoying, you have to do them, and you would love them to be generic subdomains. So again, here there is no business differentiation. So to summarize, we can find business differentiation only in a core subdomain or in multiple core subdomains of the same company, which means the business will invest a lot of focus on core subdomains to make sure that they're ahead of the competition. And that makes them the most volatile. They will change the most. Generic subdomains, not going to, they will change probably because some security patches, but nothing dramatic. Supporting subdomains, these are boring problems. Who cares? These are data entry screens that have to be there. They won't change. So again, if you're dealing with a core subdomain, expect volatility there. Expect high frequency of changes. Now, these are the 3 dimensions of coupling. Now, let's see what insights can we get by combining them. And the first one is, what's the first one? Strength and volatility. So the higher the strength, the higher the probability of cascading changes. The higher the volatility, the more often we'll have to take care of those cascading changes. So when both are high, expect high maintenance effort for that relationship. Strength and distance. Oh, this is the annoying one, because strength increases the rate of cascading changes. Distance increases the cost of implementing such change. So high strength over high distance means high cost of evolving the system. And finally, distance and volatility. So here we have distance, which increases the coordination effort. And when we couple it with a high distance with high volatility, we get high coordination effort. Communication overloads between distant teams in the company. Now, that's still not the whole picture. We can get the whole picture if we combine the 3 dimensions together. And if we do that, we can evaluate the pain you are going to go through when you will have to maintain that relationship over time. Now, I love the term pain because it's vivid, it's funny, but the grown-ups usually say cost of coupling. So if you're a grown-up, you can use cost of coupling. Can be evaluated by combining the 3 dimensions together, but come on, maintenance pain. So how can we evaluate that pain? Well, it's simple. All we have to do is multiply them. Strength times volatility times distance. Do we want high pain? There's no it depends here. Do we want high pain? Yes? No?
Job security.
Job security. That's Fortran and COBOL from structured design. So yeah, let's assume that we don't want high pain. So to minimize pain, what do we have to do with this equation?
Distance, if the volatility cannot change.
Yes, but more, let's...
Try to make zero. Just use zero somewhere.
yeah, exactly. Yeah, one of them, make them 0. Let's see some...
No pain.
Yes, and then the whole pain thing is going to be 0 as well. So let's say you have 2 components located in different microservices, and let's say both of them are core subdomains. So we get high distance, high volatility. But if they're integrated through contract coupling, strength is low, pain is 0. Awesome. What about distance? Let's say that we cannot reduce that integration strength. For example, we have functional coupling, and it doesn't matter how many hoops through the air you're going to make, the business requirements will still be there. There will still be functional coupling. Yeah, exactly. Bring them closer. Yeah, reduce the distance. Make them part of the same component, so yeah, they will change together, but it's almost as if one component is being changed. And yeah, here, this relationship with strength 0, that's what we usually call loose coupling. This relationship with distance 0, that's what we usually call high cohesion. Cohesion, which is, by the way, based on coupling, as it turns out. And finally, we have this combination that I call pragmatism. So let's say you're integrating with a legacy system. Legacy means legacy, it's not going to change, so volatility is 0. It's a different system, that means distance is 1, it's high. So do you want to modify the source code of the legacy system to introduce an integration contract, or can you just go ahead and introduce intrusive coupling? Yes, you can. That's pragmatic combination here. Again, as long as volatility is 0, it's okay to introduce high strength over high distance. So overall, here's the algorithm. First, eliminate accidental coupling. That means reduce strength to the lowest possible level. Again, not always you can reduce integration strength to contract coupling. Sometimes you need to share the functional requirements or the model. Yeah, sometimes you will need higher levels of integration strength. So go as low as possible, but come on. Going to contract coupling, that's not the goal. It all depends on your business domain. That's me wearing domain-driven design hat. So you reduce that integration strength as much as possible. What's left is to balance the distance. If both strength and volatility are high, reduce the distance. If strength is low and volatility is high, increase the distance. That's it. Now, I still have a few more minutes, so I want to show you something else, something that wasn't planned. Now, in the book, there's going to be another equation, which is going to be more complicated. And that's because here I didn't have enough time to talk about complexity. In the book, I have 2 chapters about complexity. So just remember that you don't want to have both strength and distance to be low when you have high volatility, because then you will just end up with a monolith. You will put unrelated parts because strength is minimal in the same component, distance is minimal, and it all changes because of high volatility. So it's not reflected in this equation. In the book, there will be much more complicated equation. Just remember it. That's one exception to this rule. Okay, so I still have 2 more minutes. You know what? Let's talk about microservices a bit more. So I've heard this story many times of a company. Let's say 10 years ago, their CTO read a blog about microservices, and that's it. That's our company strategy. We need microservices, right? That's how it happens usually. And so they said, okay, we're reasonable here, so we're going to do a little POC. We'll extract a few microservices, see how it works. And they do. And they say, okay, it's awesome. It really works awesome. Let's decompose it all. And then they end up with those distributed piles of code. What happens? Well, usually what happens is they choose some suboptimal decomposition strategy, which results in high strength. For example, 10 years ago, people were seriously talking about microservices being at most 100 lines of code. True story. So that's high distance, microservices, high integration strength, because yeah. But when they were doing that POC initially, did they do it with some core business functionality or a supporting subdomain? Of course, supporting subdomain. So they had that relationship balanced by low volatility, and then they proceeded and boom, they got microservices all over the place. So with that, I will do a little wrap up. So I started by defining that coupling is an inherent part of system design. There is no way to avoid it. Without it, you cannot design a system. And that coupling happens in 3 dimensions. We can evaluate the dimension of strength using this model, integration strength, 4 levels, 4 types of knowledge that can be shared between connected components. Then we have distance that reflects the collaboration effort that is needed to change the components, and also the lifecycle coupling between them. Volatility reflects or describes how often will the coupled components actually change, and yeah, as I said, there are different models. I use domain-driven design because that's me. Subdomains, core subdomains are going to change the most. And we can combine them together to evaluate maintenance pain. Strength times volatility times distance. Remember that you don't want strength and distance to be low while volatility is high. That's an exception. So that's the maintenance pain function, and this is my pain function. When it will be published eventually, hopefully in a few months, as I said, the equation is going to be more complicated, and there will also be degrees for each level of integration strength. There will be a deeper dive into each level so that you will be able to compare different integrations of the same type. If you are in Switzerland, in sometime in December, I think, in December, I will do a domain-driven design training. Let me know if you want to attend. I have a voucher, and with that, time for questions.